Okay, I think it's more or less stable now, the number of participants. So good morning, everyone. It's a pleasure to start this session with Juzar, who will tell us about the effect of measurement on Otto engines. Thank you.
Okay, thanks a lot, Marty, for this introduction. And so just a little bit further, I'm from the Institute for Basic Science in Daejeon in South Korea. And what I'll be talking about is how measurements will affect the performance or the performance metrics of this quantum Otto heat engine. Now, this work was done in collaboration with Jung-Rok-son, who is an undergraduate at the Seoul National University, and Peter Dockner at the University of Augsburg. So here's a brief outline of my talk. I'll first introduce the notion of generalized measurements. The idea behind this would be to sort of build a physical picture on how quantum systems can actually be measured. And once I go through that, I will introduce a scheme which I'll call as repeated contacts. And this particular scheme will be used to calculate the sum of the value of an observable rather than an observable itself. So it could be quite useful in cases where you need to calculate certain sums of the values. I'll apply it further to the quantum Otto engine, and then I'll finally summarize my talk. So let me start with this notion of generalized measurements. This initially came from von Neumann and many others. And the idea seems to be very physical and intuitive, and hence I wanted to put this in terms of pictures rather than equations. So throughout this talk, there are a lot of technical details which I'll skip due to the time limitations, but you can always go back and you can either ask me or refer to the papers, for these technical details. So the idea here is that if you have a quantum system and you would like to measure it, what you need is something called as a pointer, which is nothing but a free particle. And at time zero, this pointer will have some basic spread of the wave packet. Now, the spread determines the sort of precision of your pointer. So if the experimentalist can prepare this pointer in a very narrow wave packet, the more precise the measurements will be later on. Then you let the system evolve. So the system basically evolves unitarily, but the pointer also evolves during this time. And this wave packet which the pointer had will actually start spreading. The rate at which it spreads is basically something called as a standard quantum limit, which goes inversely proportional to the mass of the pointer. So now you can immediately see that if I build a pointer which is extremely heavy, this spreading will be minimized. And basically your pointer will have the same spread as that it initially had, which means you can get precision of the same kind that your experimentalist initially built the pointer with. So typically what one looks from a theoretical perspective is this mass to be really very large, not technically infinite, but just something very large, much such that the precision of the pointer is maintained. And now, importantly, in order to make the measurement on this quantum system at some time capital T, you connect the system with the pointer. This connection is made in such a way that this interaction Hamiltonian contains the system part, which is the observable you would like to measure. So for example, if you would like to measure the energy of the system, this M here would be replaced nothing by just the Hamiltonian of the system. This P is the momentum operator of the pointer. And as you'll see in the later slides, you need the momentum operator coupling to the pointer because this will lead to basically a translational state of the pointer. And so just in very simple mathematical terms, what this means is that if I start with an initial condition of the system, psi, and an initial condition of the pointer, phi, it initially evolves, which is what you see here. This is just the unitary part of the evolution, which is underlined. And then the V is the interaction part, which is given by this interaction Hamiltonian, M tensor product E. The kappa decides the strength of the system pointer interaction and also the time scale at which the system and pointer interact. Now, since this is the momentum operator P, what happens is that in the position representation, the pointer state phi of x simply gets translated. And this gets translated by the eigenvalue of the operator m. And hence, in order to make measurements, all you need to do now is basically to measure the pointer using a projective measurement, and depending on how much it has shifted in the position, you would come to know what is, or you would rather infer what is the outcome of the measurement of this quantum system. So let me quickly go on to a scheme within this sort of generalized measurements framework, which we'll call repeated contacts. Now, in many situations, what happens is that you just don't want to make a single measurement, but you want to make measurements many times onto the system, because you want to calculate the sum of certain observables. We'll see a very specific example in terms of the quantum Otto engine in the end, where you want to measure the work output after every cycle, and you want to do this for n cycles, let's say. Okay? So in this scenario, you could either basically measure immediately the pointer after every time it interacts with the system, which would be a repeated measurement, or you could wait and just let the pointer keep interacting with the system repeatedly. Due to these repeated interactions, the pointer will actually gain information about what was supposed to be measured, and then finally you measure the pointer, which we'll call as a repeated contact scheme. I'll illustrate this repeated contact scheme in the next few slides using some illustrations. So the idea in repeated contacts, as I was mentioning, is that you start with the system at time 0 and you're evolving it till time t, and this is basically the dashed line is my pointer state. Initially, you start decoupled. So the system and pointer are completely decoupled, rho being the system state, sigma being the pointer state. And we'll keep track of this completely positive linear map, which will help us decide what is happening. Okay, so initially we are at rho tensor product sigma. I just make a contact at time 0 between the system and the pointer. You need not do that. I mean, it completely depends on what one needs to measure. But in this example, we make initially a contact between the system and the pointer. Due to this, the state basically gets modified by this V operator, which was my interaction operator. You let the system evolve unitarily, and then at some capital T, you again make a measurement. So, or rather you make a contact, sorry, with the pointer. You keep doing this repeatedly. So you have used the same pointer and made multiple contacts with the pointer. And then finally, what you would do, is you would actually measure the pointer out. Okay? So this measurement of the pointer means that you would actually take the projective measurement in the state x of the pointer. And this is what you see here, that you measure at the very end, you let it evolve using this V and U combinations, depending on how the point and the systems evolve. So in the spectral representation, what one can do is write this completely positive linear map, and actually this will be related to the probability distribution function. So given the Hamiltonian, which has a spectral representation with P being the eigenstate and Et being the eigenvalue, and the measurement operator having, again, a spectral representation, what we assume now is that the sigma, which is the pointer state, is a Gaussian, and this will help us tremendously in simplifying some of the problems. And I've cut out all the maths in between, but what you get finally is a complicated looking formula that I would like to point out to 2-3 subtleties here. So this positive linear map now has this sigma, which was my pointer state, and this pointer state has been shifted. The shift in this pointer state is given by this Sn, which is not the single eigenvalue of the measured operator, but the sum of the eigenvalues. And this is why I mentioned that this repeated contact will be used to measure sum of certain values of the observable and not a single observable itself. The D here represents some amplitude coefficient which gives you overlaps between your, the eigenvalues of your Hamiltonian and the eigenstates of your Hamiltonian and eigenstates of your measured operator. So there's an amplitude and an overlap coefficient which is highly complex, but the key point here is that you basically shift it by the sum. More importantly, the variance of this Gaussian remains the same as the initial variance. Okay? So it does not change. There's only a shift in the Gaussian, but the spread of the Gaussian does not change. So the pointer does not lose its precision. And once you have this, what you can do is you can calculate the probability distribution function of observing the pointer in the state X, which is nothing but tracing over the system of this completely positive linear map. And this gives you the final probability distribution, which again, naturally would be shifted by the sum. The other contrast to this would be the repeated measurement scheme, in which you measure the pointer immediately as soon as it has made a contact with the system. So for example, here you make a contact between the pointer and the system and you immediately make a measurement out of it. You keep doing this, but the disadvantage to this scheme is that, of course, you need multiple pointers. Okay, so depending on the number of measurements you want to make, that many pointers you would require. And the fact that you're measuring it out is reflected in this completely positive map, because you see this O of x0, which was the projected measurement of the pointer. So depending on the pointer number, whether it's 0, 1, 2, or n, you see this basically projected measurement on the pointer. Okay, so if you want to make a comparison now, so let's say you want to measure the sum of this variable, of this observable, and you want to make a comparison between repeated contacts and repeated measurements, what you find in the probability distribution function that they look somewhat similar. So this is the probability distribution for the repeated contact scheme, whereas this is the probability distribution for the repeated measurement scheme. The amplitude coefficient looks more or less, it's exactly the same, but in the repeated contacts, you just had this Gaussian state which was shifted. And here you have this a little bit complex Q function, which is a Gaussian state, which is again shifted, but the variance of this Gaussian state increases depending on the number of measurements you make. And this is very important, because if you tend to make many measurements, the outcome of this would be that the Gaussian, or the pointer Gaussian state would be completely spread, and you'll lose all precision of measuring the system or making any sort of measurements. You have this other complicated exponential function as well in the repeated measurement scheme, which does not play a very crucial role. We'll see why this spread in the Gaussian matters as we go along. Okay, so this is a very simple example. You take a two-level system. The measured operator is sigma x, so it does not commute with your Hamiltonian. Your Hamiltonian is just z. And what you see here is you see the number of measurements. So n is the number of measurements. So this is 5 here. And sorry, these are typos here. SM actually, so the red curves represent the repeated contact scheme, and the black curves represent the repeated measurement scheme. And what you find is, even at a very small number of measurements, like 5, the repeated measurement completely sort of loses all information. Okay? It spreads out and it becomes like a Gaussian distribution. Whereas the repeated contacts still shows this nice discrete peak structure. And what you see here on these panels B, C, E, and F are for some very special values of this tau, which is your evolution time, okay? Where you still see the spread, but here in these cases, one could actually get the analytical results out of it. This is for a non-typical value of tau here. So this is for 5 measurements, and this is what you see for 8 measurements. Okay, so let me come to the Otto engine and quickly explain why this is important in the context of the Otto engine. Now, to the community here, I don't need to explain the Otto engine too much in detail, but I will just pictorially focus here, where what we have is a compression stroke, a connection to a hot bath. So this is a very standard Otto engine. the expansion stroke, which is the second work stroke, and a connection to a cold bar. And in order to measure, what we are going to do is basically use the energies of the system as our measurement operator. The reason why we need 2 pointers, even in the repeated contact scheme, is simply because you want to measure work and heat separately. So they cannot be measured simultaneously, as we'll see. So you want to measure these separately out. And the first pointer here, the black one, will be measuring the work, because as you can see, it connects to the basically, I mean, it makes a connection to the system depending at the end of each stroke, whereas the heat pointer only measures on the hot bath strokes. And now, in order to get from this measurement of energy to thermodynamics, this is also something quite standard. So what we'll do is basically in the work stroke 1, the amount of work done is nothing but the change in energy, which is E1 minus E0. So these are the states. So this is state 1, state 2, state 3, 0 prime. And similarly, in work stroke 2 is E3 minus E2. The heat is E2 minus E1 and E0 prime minus E3. Now, this is one particular cycle of the Otto engine. We want to run it for many cycles. And we want to see what is the effect of this number of cycles on the performance of the Otto engine. So at the end of each cycle, you want to know what is the work output of the cycle, and then you want to continue running the Otto cycle in this case. And what you have here is you have the work distribution for different number of cycles. So what we do is first we basically initialize the Otto cycle and just make it run such that it reaches some form of an asymptotic state. Once it reaches this asymptote, then you start the measurement process. And what you have here is for 50 and 100 cycles. The solid curves are the repeated contact scheme. And even though the number of cycles is extremely large, you do not see any resemblance to a Gaussian whatsoever. This is still a very well-defined structure, whereas the dashed line is the repeated measurement, which has sort of become a Gaussian completely. And it has lost all sort of precision on the amount of work. So whether the work is here somewhere around -5 or -7, it's impossible to tell from this repeated measurement scheme. We can change the time, meaning the time in the work strokes and the time in the heat strokes, and optimize the engine to get a maximum work output, which is what we do here. And even in the limit of these number of cycles going to infinity, one can actually calculate these things analytically in this case. So this is a comparison between repeated contacts and repeated measurements. Although they look very similar, if you look at the average work output, the repeated contacts always outperforms the repeated measurement, no matter what the number of cycles. This is the reliability of the engine. So the reliability is the average work divided by the variance of the work, which means that if your engine is reliable, so your variance should be low, in the work output. If the variance is very high, your engine becomes unreliable, sort of. And even in this case, in the reliability, the repeated contact scheme outperforms the repeated measurement. Going from the previous graph of looking at the maximum power output, it's again the same story where repeated contact outperforms repeated measurement. Now, in this cases of the reliability, the reason behind this outperformance is mostly because of this change in the variance by a factor of n. Whereas here in repeated measurement and repeated contact, in case of the work, the reason behind the outperformance is because the repeated contact allows the coherences to remain in the system, whereas repeated measurement kills the coherences, because the moment you measure, you kill the coherence immediately. And so this is sort of the main reason why.
Juzar, sorry, yeah. I'm just taking over quickly from Matthew, which was some problem of connection. Yeah, you have 20 minutes, so your time is already almost
Yes,
gone. So
I have come to the last slide.
okay,
Sorry for
sorry.
this.
Thank you very much. No problem.
Yes. So the repeated, so I proposed this repeated contact scheme, which was used to infer the sum of the values of an observable. The main idea here was that the repeated contacts as compared to repeated measurements gave a much narrower Gaussian width for the pointer, which made the measurements more reliable and precise. In case of the Otto, when you have to have several measurements, in case of running over N.Cycles, what we found is that this repeated contact, since it lets coherences preserve into the system, it gives a much higher power output as compared to repeated measurements, which kills these coherences. And also the spread helped in getting better reliability for the repeated contact as compared to repeated measurement. Yeah. So with that, I would like to thank you all for listening, and maybe if you have a question, I would be happy to answer.
Okay, thank you very much for the nice talk. Are there questions?
There is question in Q&A facility from Sebastian.
Sorry, because I disconnect. Sorry, but I disconnected because I lost noise, so I cannot see the.
Okay. Let me read it.
Yeah. Thank you.
Have you some thoughts on how to relate your analysis to the Zeno or rather quantum watchdog effect?
So at least the generalized measurement has been related to rather the anti-Zeno effect. And I think this was a paper by Magazu and Tockner and somebody else back in 2000, maybe 16 or 17, if I'm not mistaken. So there have been some connections done, but the repeated contact scheme has not been related to these effects yet. So this would be an interesting sort of point of view to get into, but we have not done this so far.
Are there more questions? Okay, otherwise, in the meantime, I wanted to ask something. So there are also these approaches where people take a weight to kind of quantify the amount of work on the whole distribution. So do you know how it relates to I would expect it's similar to this, actually.
You mean like a flywheel or something like that?
For example, yes.
Right. So this is exactly the question we are trying to address now, because what we are interested in is, so there are two ways, if you have a quantum auto engine, you either measure the work or you let it perform work on something. And whether are these two ways similar or they are completely different, we don't know yet. Okay. So the next question would be to look at this flywheel and see what comes out of that.
I see. Thank you. Are there more questions? Okay, otherwise we can start moving to the next talk. Before, so there's